So did it start? Yes. Fine. So let us look at some exercises for today. So is my screen visible?
Yes, sir.
Yes, sir.
Okay. Okay. So this week actually there was a small personal doubt which I hopefully clarified by sending an email. And there were a couple of doubts about the same thing. Using the pumping lemma, prove that set of all W in 0 AB star such that the number of A's and number of B's in W are the same. This is not regular. So I have used some kind of closure properties in order to prove that this is not regular. Given that we have proved that A power n, B power n language is not regular. Okay. Using some closure properties, we prove that this is also non-regular. So how can you do it using pumping lemma? No, this is not really a difficult thing. You can, for example, if K is the pumping lemma constant, you can actually take the string, let us call it alpha, A power K, B power K. Now there is a catch. I have to somehow decompose it as X, Y, Z with length of Y greater than equal to K. It may be K, it may be 2K. So one possibility is I can take the entire thing as Y, X empty, Z empty. This is a possibility, right? X empty, Z empty, Y is the entire thing. Now, if I try to apply the pumping lemma, I see that there is a problem. Y gets a decomposition of the form U, V, W. Okay. So it may be that this V, it is non-empty. This is what is given. This is actually not a problem in this context. This will also actually work. Yes, this will actually also work. Anyway, B is non-empty. So we can also make use of the fact that the total length of UV must be less than equal to K. So what does it imply? How will V look like? What will be V? It's non-empty.
Only A.
It will consist only of A's. Okay. So V will be something like A power L for something like this. Okay. Then if you pump in A power L, the number of A's will be more. If you pump out, the number of A's will be less than the number of B's. Okay. So in this form, this also works. You can also work with something like this. You can take X equal to A power K, Y equal to B power K, and Z empty. You can also take X empty, Y A power K, and Z B power K. Okay. And in each of these cases, you can arrive at a contradiction. Okay, so this is something like this. A power K, B power K. This is what I meant. Okay, here also, this Y, this V will consist of a few number of B's, non-zero number of B's, and therefore, if you pump out, the number of B's will be less. If you pump in, the number of B's will be more than the number of A's. Similarly here, this y, the v will also consist of only some number of a's. Okay. Therefore, if you pump in or pump out, then you are disturbing the number of a's. Okay. So, yeah, so that's the proof. Yeah, any questions?
Sir?
Yep.
So the choice for XYZ is we can choose any one and we can proceed.
Yeah, any one of these. You
But
can
the
take
choice,
these or these. A single contradiction is good enough. Okay. But I mentioned all the three possibilities because all the three things work in this context. But in some other context, it may be that you have to take something like this, and this will not work, this will not work. Or you may have to take this will not work, this will not work. It may so happen. Okay. Okay, in this case, of course, we are lucky because all the three things work. Provided that we make this assumption, the length of UV less than equal to K. In our book, perhaps this extra condition is not added in the pumping lemma. So if you follow the version of the book and if you do not use this extra constant, then this will not work. Anyway, don't worry. We can always use this condition. Okay. Of the
Sir,
different.
how are we getting alpha is equal to a to the power k b k? Like,
What is the question? The number of A's and number of B's must be equal. So I can take A power K, B power K. This initial string is our choice, right?
okay.
Okay, so once again, let me highlight. It's a game with the daemon. So you, daemon. Okay, so your daemon gives K. Alpha is completely your choice. That is, you can choose X, Y, Z as you like. Okay. Then you supply that thing, only you have to ensure that the size of y, that is the length of y, is greater than equal to this k that the daemon gave. Okay. Then the daemon gives you a decomposition y equal to uvw with the given conditions. Then your choice is I. And if you can arrive at a contradiction, then you are done. And if the language is not regular, then definitely if you play the game carefully, that is, if you can choose alpha and I, then you are bound to win. Okay. The daemon cannot win. So these are only your choice. How you choose X, Y, Z, and after you get a decomposition, this is not again in your hand. But after this is given, you can choose I. K and this quantity is the daemon's choice. Okay. Okay, any further doubt about this?
Excuse me, sir.
Yeah, tell.
Sir, is there any specific advantage in choosing mod UV less than equal to K? I mean, like, can't we just choose V less than equal to K?
Yeah, you can choose. You can choose. We do not use this condition. Okay. Then, so not used. Suppose this is not used. Okay. And let us look at what happens here. The first example. So you have X empty, Z empty, and your Y is the entire thing. Okay. Which is A power K, B power K. If you do not use this condition, then it may so happen that V is something sitting at the border, something like A power L, B power L. It's possible, right? Because the decomposition is the daemon's domain. It's not your domain. The daemon may give you a decomposition of the form a power L, b power L. Okay. If that is the case, so you have something like this, a power k minus L, a power L, b power L, b power k minus L. Now, if you take this out or pump in as many times as you want, you will still have a string with equally many A's and B's. So if you do not use this extra condition and can, I would say, establish that V must be consisting only of A's, then this decomposition of alpha into XYZ will not work. Okay, the daemon may supply you some B which will never let you reach any contradiction. But if you impose this additional restriction or additional condition on the decomposition, then you can conclude that V will consist only of A's. Okay, so that is the reason why using this condition sometimes helps you. Okay. Now, if you use this decomposition or this decomposition, the second one or third one, then definitely you do not require this. Okay. But if you use this decomposition, X empty, Y, the entire thing, Z empty, then this is going to help you. Okay. So this actually simplifies the process in many cases. Yeah, tell. Is that fine?
Yes, sir.
Okay, good. Okay, of course, you can live without this. In fact, our book does not, as far as I remember, our book does not give this extra condition, although it is immediate from the proof. Okay. Okay. So this was a doubt. The next question is going to be essentially the same. So this is the beginning of the tutorial things. So now consider one of the following the two languages. Instead of AB, I am using 0, 1. So one of the following languages is regular, the other one is not. Set of all strings, binary strings containing an equal number of occurrences of zeros and ones. And by the doubt, you know, instead if I rename A as 0 and B as 1, so this is not going to be regular. We have already proved it. And therefore, this must be yes. Okay. So we have already seen this no. Therefore, this has to be yes. So this is an interesting thing. Set of all strings containing an equal number of the patterns 0, 1 and 1, 0. It is, however, regular. Actually, in order to decide, or I would say, whether an element is in B, you do not actually have to count 0, 1s and 1, 0s. Okay. So counting how many times 0, 1 and how many times 1, 0 occur is not necessary. And therefore, this language is actually regular. So why? But of course, this is basically an intuitive justification. If you have to prove something is regular, what do you have to do? You have to build a DFA for it, or an NFA for it, or a regular expression for it, or later you will know you can also propose a right linear grammar for it. So how do we proceed here? In fact, what is the basic intuition?
Sir, after a continuous string of ones, if a zero occurs, then like we can maintain two states, 1 and 0. And yeah, if we are in the state 1 and we count like a 1 occurs, then it's a self loop. And if a 0 occurs, then it will go to the state 0. And for 0, the same condition. If a 0 occurs, then it's a self loop. And if a 1 occurs, then it goes to the state 1. So basically, it will move from the state 1 to state 0 when after a string of ones a 0 is occurring, or after from 0 to 1 if after a string of zeros a 1 is occurring.
Yeah.
So number of these changes should be same.
Yeah. So the idea is this: if somewhere 0, 1 occurs, then without a 1, 0 occurring, the second 0, 1 cannot occur. Right?
Yes.
Right. So that's the idea. So based upon this suggestion, I can actually build a DFA or NFA. I think this is going to be DFA. So this is the start state. Start state contains 0 patterns, 0 occurrences of 0, 1 and 0 occurrences of 1, 0. So it should be an exit state. Then the machine can read either 0 or 1. If it is 0, then as long as 0 comes, there is no problem. If it is 1, as long as 1 comes, there is no problem. Right. But if a 1 comes, then 1 occurrence of 0, 1 is located. Okay. Now, as long as 1 keeps on coming, I can still see no pattern 1, 0. So whenever 0 comes, I will go back here. Okay. So this is actually here also, whenever 0 comes, I have seen 1, 0, but I have not seen a matching 0, 1. And as long as 0 keeps on coming, there is no problem. Whenever 1 comes, I have seen a matching 0, 1, and I will come here. So this is basically a DFA for accepting B. So although these two languages A and B look quite similar, they are actually quite different. Okay. Although I say equal number, here counting is necessary, here counting is not necessary. But in order to establish whether counting is necessary or not, you have to give some proof, either in the form of pumping lemma, if the answer is no, or in the form of a construction of DFA or NFA or regular expression, if the answer is yes. Is that clear?
Yes, sir.
Okay, so I will switch to the next one. Once again, I believe it's an exercise where two apparently similar looking problems, one of this is regular, the other one is not. So once again, I am talking about the count of A's in X and count of B's in X, and I am combining those and I'm trying to equate those. So the difference is that here there is no separator between X and Y. Okay, so that the number of A's in X is equal to number of B's in Y. Here I have a separator $, some third symbol. Okay. So one of this is going to be regular, the other one is not, although they both involve counts. So what is your initial intuition?
A is a regular set and B is not.
A is regular, B is not. What makes you think so?
If A contains even number of A, then we can just set a separate X and Y at the midpoint of A's, count of A's. We can make a parity check over A.
Parity check will not just suffice because
We had the choice of X and Y in yes.
equality of count. Yes, you have a choice of X and Y. That is true. So
if we have even number of A's, then we can separate them with equal number of A's in two parts.
okay, fine. But what will happen to B's? I am equating the count of A's in this part with B's in the second part. Okay, okay. I think I made a mistake. This is a mistake. Sorry, I will just correct it. Sorry. Why? Sorry, the question was wrong. Yeah, this is the correct question. Number of A's in X is equal to number of B's in Y. Sorry for the confusion. Yeah. Yeah, no suggestions? we can use the pumping lemma for the first part by taking the string a power k, b power k. So here is the suggestion. So A is not regular. This is a suggestion. And pumping lemma, if the constant is k, okay. So what is your x, y, z?
Like in the previous question,
Which one?
like take x to be empty, y to be a power k, and z to be b power k.
Okay, this is y and this is z. Okay, x is empty. Okay. Then the daemon gives something like this. V will be something like, okay, so you have a power k plus minus I L, or y plus minus, sorry. Okay. B power k. It will be something of this form, right? For some L. You can take I equal to -1 or 0, 1, 2, 3, everything. Okay. Now I suggest this decomposition. Let's say, let us take I equal to +1. So we have something like this: A, k plus L, B plus L. Sorry, B plus k, B power k. Okay. So if I decompose it this way, A power k, B power, sorry, A power L, B power k. The number of A's here is k, number of B's here is k. So it is in A. If I take a string, if I take I equal to -1, so if I have something like this, power k minus L, B power k, I can decompose it as A power k minus L, B power L, B power k minus L. So number of A's here is k minus L, number of B's here is k minus L. So do we really arrive at any contradiction?
No, sir, but now it became clear that why the dollar was necessary over there.
Why?
With an explicit dollar in the between, if the construction is of the
Yes.
form a power k dollar b power k, then we can no longer like shift a's and b's.
Yes. On two
as we
sides
did.
dollar, from this side to another side. Yeah, that's true. So this proof will actually work for B. Okay, so B is not regular. So I can take something like A power k dollar B power k, where k is the pumping lemma constant. And like your suggestion, I can take this y, this entire thing z, x may be empty. And then if I pump in or pump out some A power L, okay, then this is no longer satisfied. But what about A? There is in the first case, if length of y is total number of a's in xy, then xy belongs to A. We can use this. If the first case, if length of y, total number of a's in xy, don't understand what you mean. A should be sigma star. There must be a point in any string where you can divide it to satisfy the condition. Exactly. So proof. How do you prove? Okay, maybe by induction on the length of strings in A comma B star. Okay. So take any W and show that W can always be decomposed in the form XY such that the number of A's in X is equal to number of B's in Y. So if W is epsilon, then definitely I can write it this way. Okay. Otherwise, I have to do a little bit of work. Now suppose a given W has a decomposition X, Y. Then I consider two cases. This is an A, this is an B, this is a B. Okay. If this is A, I will keep the decomposition X, Y, A. Okay. This is the case. Now the decomposition X, Y, A will work. Because you are adding an A to the Y part, but I am counting B's in the Y part, so it doesn't matter. And what happens here? Now definitely X comma YB, this will not work because the number of B's will be just one more.
Sir, we shift the partition by 1 to the right. If it's an A, then the number of A's will increase in X. If it's a B, the number of B's will decrease in Y.
I look at this. And I will just move X, okay, by one position. What does it mean? It means that if this symbol is A, then by shifting this partition X by one cell, I'm increasing the count of A's in that part. And if I include B in that part, so I'm losing one A, it doesn't matter, but I'm adding one B here. Okay, so that is fine. If this is B, then again, if I make a shift, what will happen? I am decreasing, I am compensating for the addition of this B by the loss of this B. Moreover, B is added to X, it doesn't matter, I'm counting A's. Okay. So in this case, shift the partition. One cell right. But is this proof complete? Is the proof still complete? So of course, this can be either A or B. Here it can be either A or B. But okay, so there is some other logic. Maybe this will work. But anyway, let us complete this proof. It's inductive proof. y can be epsilon. That's the question. So if y is epsilon, then this will not work. Okay. So here I have made an assumption that there is something here. Okay. So that leaves us with the third case, y is epsilon. So if y is epsilon, then what will be x?
A string of all b's.
A string of b's only. So I have now a situation like this. B power k, epsilon, and a b has come. Okay. So what should I do? In this case also, I can have a decomposition. Okay, I will again expand x to include this new b. Or I will continue to stay as epsilon. Okay. That's it. Okay, so shift the partition one cell right, provided that this is allowed in y. If it is not allowed, then also this case can be handled separately. Okay. Okay, so this is once again an interesting question. So you see that this separator is quite important. That's a good suggestion from you, so that you cannot move this partition from here to here. That is the reason the second language is not regular, the first one is. Yeah, any further queries? Okay, then let us go to the next question. I have many things ready. Anyway, let's see. It's a big statement. Okay. So let us consider a set of positive integers. Also, you can take non-negative integers. Okay. N or N0. Okay. Now consider A is a set. Okay. Consider the set of all binary representations of elements of A. So since this is a binary representation, so these are strings consisting of zeros and ones, bits. Okay. And you also take this set of all unary representations. So I will use 0 or any other symbol for that matter. So 0 power n, n belonging to A. So this is now a language over the unary alphabet 0. Okay, so now I am telling two statements. So this is a language over 0, 1, this alphabet. This is a language over the singleton alphabet 0. Okay. So now I claim that, or I state two things. If binary A is regular, then unary A is regular. This is statement A. Statement B is, if unary A is regular, then binary A is regular. One of this is true, the other one is false. Okay, so I have already told a little bit about it. Okay, so one is true, the other one is false. Which one is which and why? The second one is true. Why?
Sir, if unary A is regular, then we can say that the set A is ultimately periodic.
Yes. Okay, that's okay. Okay, so I have to use ultimate periodicity. Okay, I would not say I have to use. So a good way to solve part B is using ultimate periodicity. And therefore, since that is true, okay, so this is true, therefore this has to be false, because as I mentioned, one is true, other one is false. So which one shall we tackle? Maybe the second one, because this question, this answer came earlier. So if this is a regular, then A is ultimately periodic. Okay. So what does it mean? So there is some N0. Here I may have some smaller than N0. I may have a few individual elements like A1, A2, up to let's say a K. And then I have a period P. So from this point onward, if some number is in A, then that plus P will also be in A, and conversely. Okay. So here I will find a set of numbers B1, B2, BL. Okay. So I can write A as the union of some A1, A2, AK, union N such that N is congruent to some B1 or B2 or something like BL modulo P, and this N is greater than or equal to N0. So that's the definition of ultimate periodicity. Before this N0, there may be some random things. I would not say random, any arbitrary things. But after this N0, at this point N0 onward, only these modulo P numbers B1, B2 up to BL will keep on appearing. This is true. This is ultimate periodicity, right? By definition of ultimate periodicity. And then I have to somehow design a DFA for this binary A. This part you know how to handle. Do you know or not? For example, we have seen multiples of 5, multiples of 3. In a similar manner, I can say multiples of 5 plus 2 or multiples of 5 plus 4. So you have 5 states. Okay. Depending upon the modulus, we have 5 states. 0 modulo 5, 1 modulo 5, 2 modulo 5, 3 modulo 5, 5 modulo 5. Okay. And whenever you have a new symbol, it may be either 0 or 1, depending upon that. So you have a switch from one modulo P state or modulo 5 state to another modulo 5 state. So I have something like this. Maybe something. So this is 0 modulo P, this is 1 modulo P, 2 modulo P, P minus 1 modulo P. Okay. And I have B1, B2, BL, all are in this number 0, 1, 2 up to p minus 1. Whichever appear, I will make them final. Maybe this one, these are final. Okay. And then if you are in this state, if you read 0, 2 times 0 plus that, this will be here itself, right? If you read 1, it will be 2 times 0, 1. Okay. You know how to do this part, right? Yes or no? So you have seen examples like modulo 3, modulo 5. Okay. Now I have a general situation. I have B1, B2, BL. Okay. So whichever things are appearing here, so I will just make these corresponding states final. Other things will be even non-final. Okay. Is that clear? This part? But I have not yet factored this condition, n greater than equal to n0. But if I do not have this construction is fine, right? Yes or no?
Yes, sir.
Yes, right. Okay. So instead of modulo 3 or 5, I'm just working in a modulo p for some period p. Now, how to handle this part? Okay. So this part is also not that difficult. I will just make a complete binary tree of this form. 0, 0, 0, 1. So this stands for epsilon. This is 0, this is 1. This is 0, 0, this is 0, 1. This one will be 0, 0, 0, 0, 0, 1. 0, 1, 0, 0, 1, 1. Here 1, 1, 0, 1, 1. 1, 0, 0, 1, 0, 1, and so on, right? So for all numbers less than equal to less than n0, I can build a complete binary tree. And then if multiplying by 2 or multiplying by 2 plus adding 1 lets that number become greater than equal to n0, I will no longer branch in that tree. Instead, I will simply redirect to the appropriate modulo number here. Okay. So if it is not clear, I will give you a more explicit example. Please let me know.
No, sir, how are we transferring from this part to that part?
Oh, okay. Maybe it's better that I give you an explicit example. So this will illustrate what it. Let's consider this. A is something like union. Let's say n congruent to 1 or 3 modulo 5 and n greater than equal to, let's say, 8. Or maybe I will not take it 8. 7. 6. And here maybe I have 1. No, I would not take 1. Maybe I will take 2 and 4. 2 and 5. Okay. So let us first draw the modulo 5 loop or modulo 5 part. 0, 1, 2, 3, 4. Okay. 1 and 3 should be final. So 1 and 3 final. Okay, so now just add these things. 0, 1 comes, If I have 1 here, so it is already of the form 5k plus 1. Then if a 0 comes, it becomes 10k plus 2. So I will come here. And if 1 comes, I will come here. Okay, you can complete this part. This is the initial thing. Now here, I have to consider all n less than equal to 6. Okay. Less than 6. So 0, 1, 2, 3, 4, 5. This is 0. One, 0, 1, 2, 3, 4. Okay. 6. So this essentially stands for 0. This stands for 1. Sorry. This stands for 0. This stands for 1. This essentially stands for epsilon. This is 0, 1, 2, 3, 4. Okay, so 5 I should also have. And 2 and 5 should be accepting. So this 2 is accepting. 5 is accepting. Okay. Then no. Leading zeros are creating problem. So let us do one thing. Leading zeros are creating problem. Or maybe I just select this. Okay, so leading zeros are creating trouble. So I have something like this. So leading zeros you just absorb here. Then you can have only, so this is 0. This is 1, 2, 3. Four, 5. Okay. So 2 and 5 should be final. So I mark them. Then if I read a 0, 4 times 2 is what? 8, right? But 8 is greater than or equal to 6. So if I now read 0, okay, 4 times 2 is 8. 8 modulo 5 is 3. So I will go here. And if I did 1, 4 times 2 is 9. 9 is modulo 5, 4. So it will come here. Right? For example, here again, 3 times 2 is 6. 6 is 1. So if I read 1, I will come here. Sorry, 0, I come here. If I read 1, I will come here. Okay, so likewise you give these two links. So initially we have this non-periodic part, and then you will keep on wandering in this loop. I mean, this is not a loop, but anyway, wandering in this part. Is this construction clear now?
Yes.
Okay. Okay, 1256. Oops. So this is actually an example of ultimate periodicity. But what about this? Binary A is regular. Then this is regular. So you have to give an example of a set A for which this is regular, but this is not regular. 2 power. Yes. Good. Good. So maybe I take A equal to 2 power n. And what is binary A? It is basically the language of 1, 0 star. And if you allow leading 0 bits, it's something like this. Yes or no? Basically, this is 1 followed by an arbitrary number of zeros, 0 star. Okay. Whereas unary A is not regular. You can use the pumping lemma. Yeah, we have already proved that this is not regular. Or maybe we have proved it for 2 power n or n square. Anyway, it's the same similar proof will work. Okay. So yeah, we are running out of time. Maybe next exercise, let us just take a look at it. Okay. Prove that no infinite subset of A power n, B power n is regular. Okay, so I'll just give you a hint. So let L be an infinite subset of the given set. Okay. And assume that this is regular. Suppose and then let K be a pumping lemma constant for L. Okay, now since L is given to be an infinite set, so all strings in L cannot be of length less than K. Is that clear, right? So L infinite implies L contains strings of length greater than K or greater than 2K, whatever. Greater than equal to K or 2K, whichever. Both are true because K is a constant. And if I look at A power n, B power n type of strings whose lengths are less than equal to K or 2K, they will be finite in number because K is a constant. Okay. So now I can take some A power T. Not T is not good. Take any A power M, B power M, N, L with M greater than equal to K. The infiniteness of L implies that such a string exists. This is fine, right? Okay, then proceed. As before. Now follow exactly the same thing. Instead of taking A power K, B power K, I am taking A power N, B power N. Okay, that's the only difference. So I will just read this. Prove or disprove there exists a language over the alphabet A, B has that no infinite subset of L is regular and no infinite subset of complement of L is also regular. Now, what about if I take L equal to this A power n, B power n? Of course, by the previous exercise, we have seen that no infinite subset of L is regular. But what about the complement of L? Does it contain an infinite regular subset? Star. Yes. Okay. A star or a plus, whatever, it doesn't matter. Okay. It contains many infinite regular subsets. So this is not an example of such a language. Okay. Okay. So I end this today's session by saying that this can be proved. And actually there exist languages such that no infinite subset of L or its complement is regular. So as a hint, okay, so think over this. I am not telling you the solution, but I'm just giving you a hint, explicit hint. Using ultimate periodicity, you can actually locate such a language L. Not so difficult. Okay. So let us stop. It's already 5 minutes past 1. Fine, right? So we are again going to meet on Thursday.
Excuse me, sir.
Yes, tell.
Sir, since we are meeting on Thursday, so our week practically gets over on Friday itself for this course. So it would be, if it is possible for you, then it would be better if you could post the lectures on Friday night or Saturday night itself instead of Sunday.
Oh, I will do. I will do.
Okay, thank
I
you.
will do unless I have a problem. Like occasionally, I may have to go to Calcutta to attend my parents. So if I do so, then it may be difficult to do it on Friday or Saturday. But in general, it's possible. Okay. So I'll upload on Friday or Saturday.
Thank you.
So could you please upload the tutorial slides?
Tutorial slides means?
Means whatever you've done today.
Yes, I will do. You will
Thank
look
you,
at,
sir.
yeah, you just look at this file section in this Microsoft Teams. You will find it there. All the things are there.
Okay, sir.
Okay, then let us take a break until next week then. Bye.
Thank you, sir.
Okay, see you next week. Okay, so let me stop the recording. No, this is not recording.